So far, we have been talking about the Gibbs free energy in a qualitative way. We have said that depending on the sign of enthalpy and entropy, the sign of the change in Gibbs free energy may be positive or negative, making it non-spontaneous or spontaneous. In some cases, it depends on temperature. That qualitative discussion needs to happen. However, it may be also important to deal with real numbers. And to deal with real numbers, one needs to calculate the standard Gibbs free energies. So to calculate thermodynamic potentials, thermodynamic state functions, and by a state function I mean enthalpy, entropy, and Gibbs free energy, one can always build the cycle, what we call the thermodynamic cycle, the Hess law, sending reactants to the roof, sending products to the roof, and do the difference between how much energy it takes to send products and reactants to the roof. That roof, we call that the standard state. It's just a fairly arbitrary choice, but experimentally it's very easy to set up, so that's our reference point. For enthalpy and entropy, no, enthalpy and Gibbs free energy, but remember that entropy is, we have an absolute roof, if you will, that's at 0 Kelvin, so that's what you will see in your tables. We have these formulas for calculating the enthalpy, the entropy, and the Gibbs free energy, and all of these are tabulated. They can be found in data tables, so that's not much of a difference to calculate the change in enthalpy, change in entropy, with one difference. Notice that you can calculate the change in Gibbs free energy in two different ways. If you have the delta H and delta S, you can combine these and already calculate delta H minus state delta S. So you can combine the entropy and enthalpy to calculate the Gibbs free energy. So one wouldn't need to use this one. So that would be, if you will, option 1. The option 2 is to avoid going through enthalpy and entropy and look up the tables for the Gibbs of formation, the change in Gibbs free energy of formation for products and reactants. So in this video we're going to calculate the change in Gibbs free energy using these two approaches. So in this slide is just to show that yes, one can find tabulated the entropy, the enthalpy of formation, the Gibbs free energy of formation of as many compounds as you want. So one just needs to apply these equations to find the change in Gibbs free energy of any reaction. So let's do that. Let's calculate the change in Gibbs free energy, and because it's standard, that means that the temperature is at 298 Kelvin for this reaction. Well, if we use option 1, the change in Gibbs free energy, and that's for option 1, we need to know the enthalpy and we need to know the entropy. So the enthalpy of the reaction will be the enthalpy of formation of water minus enthalpy of formation of hydrogen minus enthalpy, and I should put a 0 here, and 1/2 of formation of oxygen. Because hydrogen and oxygen are already in their standard state, this both are 0, so the enthalpy for the reaction is equal to the enthalpy of formation of water, which if I go here for water, it's negative 241.82. 241.82 kilojoules, and careful here because entropy is going to be in joules, not in kilojoules. So now let's calculate delta S. Delta S would be the change in entropy of, this is absolute, so the entropy of water, standard, so of course all of these are standard, and minus the entropy of hydrogen, which is not 0 anymore, and the entropy of oxygen, and there is 1/2 in here. So one just needs to substitute. For water, the entropy of water is here, is 188.83, 188.83 minus the entropy of hydrogen. Let me see if I find it. Oh, hydrogen, right above. 130.58, 130.58, and the entropy of oxygen, it's right here, 205 minus 1/2, 205, 205.0. Okay, so notice that these will be numbers. Careful that you will need to multiply this by 1,000 so that it's both in joules, so one can just substitute this in here. The temperature is at 298, and there you go. You have calculated the change in Gibbs free energy for this reaction. The second option is just going directly to the tabulated values for the heat of formation. So the change will be the change for the heat of formation of water minus the change for the heat of formation of hydrogen minus 1/2 the change, and I say heat, but it's actually Gibbs free energy of oxygen. Notice that for Gibbs free energy the pure elements are defined as 0. Okay, so also for, let me see, oxygen is here, hydrogen is here, so these two are 0. So if you have access to the Gibbs free energy, the tabulated data, as you can see, is a much faster approach, with a caveat that this will only give you at 298. In principle, you could have calculated this at different temperatures, assuming again that enthalpy and entropy are constant. So option 1 is good when you want to calculate the change in Gibbs free energy at different temperatures, assuming again that enthalpy and entropy are constant. But if you just want to calculate the change in Gibbs free energy at the standard temperature, the route 2 is much easier, because we just need to look up the formation of water. In this case is negative 228, sorry, I missed the 57 kilojoules per mole. It's negative, it's spontaneous. That should make sense, because it's actually a very explosive reaction.